Swayam Prabha. Digital India. Educated India.
Now, let us look at how to analyze thin walled closed sections. Okay. Till now we have been looking at thin walled open sections or closed sections from which will won't warp. Okay. Now, let us analyze thin walled closed sections which will warp. For example, if I have a box kind of a cylinder geometry cross section, say I have a box shaped cross section or a elliptical cross section, or an elliptical cross section like this with uniform thickness or varying thickness. How do you analyze these sections? Because annular cylinder is a thin walled section which will won't warp because of the geometry. These sections will warp again because the shear flow is not continuous in the cross section. Okay. So, let us analyze how to analyze the structure. Okay. So, now for this we will think of it as, we will make an assumption that the shear stress at a particular section is uniform across the thickness of the cross section. Okay. What happens in a thick walled section is the shear stress across the thickness of the cross section will vary, but this being thin walled we assume that the shear stress does not vary across the thickness of the cross section. Okay. That is, if I cut here and expose, see the shear stress variation along this line, we will assume that it is constant. Okay. So, let us assume arbitrary geometry wherein the thickness also need not be constant. Okay. Some arbitrary geometry, let us assume the CG of the geometry is here. Okay. This is CG of the cross section and the center of rotation of the cross section, this is y, this is x. Okay. Now, the shear stress in this cross section, it being thin walled, even though it has a varying thickness, is tangential to the geometry of the cross section. It will be like this, the shear flow will be like this. Okay. The shear flow will be like that. Okay. Now, what I am assuming is, I am assuming that in this thickness region the shear stress is constant along this thickness region. Okay. So, now let us consider an infinitesimal element of dimensions ds here. Okay, wherein this uniform shear stress acts in that ds element. Okay. Then what is the torque for this? The torque would be given by integral tau, which is the shear stress acting in that infinitesimal element, times the area of that infinitesimal element, which is T times ds. This torque, this shear stress is a function of S. This is a function of S, because of the thickness changes the shear stress can change. Okay. This can be a function of S, okay, in general. Okay. So, basically this is tau times T times ds, okay, into, that is the net force acting in that cross section, times I have to multiply by the lever arm. The lever arm is the perpendicular distance between the CG and the, say that is a tangent to the curve at that point. Then I want this perpendicular distance, this is 90 degrees. Okay. I want this perpendicular distance, which is say r. Okay. So, that will be times that r. Okay. Now let us understand what this ds r mean, what this ds into r mean. when I integrate over the entire cross section. Okay. Now this ds times r represents the area of this triangle up to the center line of the cross section. Okay. Because ds is the base, I have a triangle like this whose base is ds, okay, and whose perpendicular distance from this point to this is r, that is the lever arm. Okay. So, now what is this, ds into r would be twice this area of this rectangle triangle. Okay. ds times r will be twice area of the triangle there. So, when I integrate it over the entire cross section, I will get it as 2 times tau t into area of the enclosed area of the cross section. What I mean by the enclosed area of the cross section is, it is the area given by, say this is the center line of the cross section, the blue line. I am interested in the area enclosed by the center line of the cross section, that is, this is area enclosed by the center line of the cross section. Okay, that is the area enclosed by the center line of the cross section. So, I have found the expression for torque. Okay. Here you have to note that even though tau s is a function of s, tau t, here I have pulled out tau t outside the integration, because tau t I am assuming is a constant. T can be a function of s, tau can be a function of s, but tau t is not a function of s. Okay. So, I have the expression tau t equal to a constant. Okay. That I assumed in this derivation. Okay. So, now we have derived the expression for the torque as 2 times tau t into the area enclosed by the cross section. Next I want to relate this to the angle of twist per unit length, right. So, for that we will take an energy approach this time. Okay. For this we have to construct the complementary strain energy. Which we introduced in lecture 15, u star, this was integral over the volume of the body 1 plus nu by 2 e trace sigma square minus mu by 2 e trace sigma the whole square into dV, the volume of the body. Okay. Now, what is sigma for this case? Sigma for this case in x and y coordinate system, this there is a shear stress in the plane of the cross section alone. So, it will have 0 0 sigma x z, 0 0 sigma y z, 0 0 0 sigma x z and sigma y z and 0 there. Okay. This is the state of stress, because I can resolve the effective shear stress tau into components sigma x z and sigma y z. Okay. Now, what is sigma square? Now, sigma square is sigma x z squared sigma x z sigma y z 0 sigma x z sigma y z sigma y z squared 0 0 0 sigma x z square plus sigma y z square. Okay. Now, next I am interested in finding the complementary strain energy, which is u star. I know that trace of sigma is 0 and trace of sigma square is 2 times sigma xz squared plus sigma yz squared, that is nothing but 2 times tau square. Okay. So, what do I have? The complementary strain energy is 2 times tau square 1 by nu into 1 plus nu by 2 E dV. Okay. From the definition of shear modulus, or from the fact that the Lamé constant is equal to the mu of the Lamé constant is equal to the shear modulus, you can rewrite this equation as integral tau square by 2 G dV or integral tau square by 2 mu dV, right. Okay. Because G equal to mu is equal to E by 2 times 1 plus nu. Okay. I have used that relation to rewrite it as this. Okay. Now, what I am going to do next is I am going to substitute for the torque from the expression here to the shear stress in here. Next I am going to substitute for the torque from this expression into the shear stress expression here. Okay. So, what do I get? I get u star to be integral T square by 4 T square enclosed area squared dV by 2 mu. Okay. Now, what is dV for this case? The volume of the body. I can write that as T square by 8 T square enclosed volume square into mu to dV. I can write it as ds into T, this is the area of the cross section, okay, times dz, which is integration along the length. Okay. So, now T alone can depend upon the axis, the axial location of the member, but let us assume that this V, here I am assuming that to write this, I am assuming that the torsion moment does not change along the axis of the member. Okay. So, 8 a square integral ds by t. Here I have assumed torque does not change along the axis of the member and the axial length of the member is L. Okay. So, now what have we got? We have got the complementary strain energy as T square L by 8 mu area of cross section squared ds by T. This is the contour integral or the line integral, this is the line integral of the cross section along cross section. Okay. Now, next I have to construct the total potential, which is u star minus the load potential. Okay. So, next again this load potential and total potential are defined in lecture 15. So, I request you to go back to that lecture if you are not familiar with these definitions. Okay. Now, load potential V is defined as T times phi, okay, because I am applying a torque T and phi is the angle of twist at the point of application of the torque. That is, I have this cross section where I am applying a torque T here at a distance L from this fixed end. Okay. So, that phi would be the angle of twist that this section, the angle of twist of this section, the angle of twist of this section is phi. Okay. That will be nothing but omega times L, where omega is angle of twist per unit length. Okay. So, that is phi. Okay. Now, the total complementary potential pi star is u star minus v, which is T square L by 8 mu a square line integral ds by T minus T into phi. Okay. Now, I want to get this phi. I know that in energy method I have to minimize the potential with respect to the independent variable. I am writing in terms of complementary strain energy. So, the independent variable is the torque or the force. So, I have to minimize this with respect to the torque, which means I have to set dou pi star by dou T to be equal to 0. Okay. So, that will give me T L by 4 mu a square into ds by T minus phi equal to 0. Okay. In other words, this will imply that phi is T L by 4 mu a square into ds by T. Okay. Now, you know that phi is omega into L. So, from here I get omega angle of twist per unit length as T by 4 mu a square into line integral ds by T. Okay. So, essentially what we have shown is for thin walled sections we assume that tau times T is a constant, that is thickness times the shear stress is a constant, that comes from the equilibrium requirement of the cross section in other words. Okay. And then we showed that the torque is given by 2 times tau T into the enclosed area of the cross section, and we have shown that the angle of twist per unit length is given by T by 4 mu a square into ds by T, the line integral along the circumferential area of the cross section divided by T, thickness of the cross section. Okay. So, this is the result that you have to remember from here. Okay.